Okay. So, in deterministic communication complexity, you are given a matrix, Boolean matrix. It's 2 to the n by 2 to the n. Every row and column is identified with a 0, with an n-bit vector, n-bit string. And we have two players, Alice and Bob. Alice has only x and Bob has only y. These two variables. And they want to figure out what is m of xy, the bit corresponding to row x and column y. So they exchange some bits, and at the end, one of them at least realizes what's that value. And the communication complexity of this matrix is defined by the maximum number of exchange of bits that they have to do such that they can realize the result. And in this talk, I'll be only talking about deterministic protocols. So there's no randomness involved. Okay. One other way of looking at communication complexity is that, okay, if you have a communication, if the communication complexity of your matrix is, let's say, k, then you can partition your matrix to a bunch of rectangles, but they are monochromatic. They are all either 0 and 1, and it's at most to the k many of those. And by a rectangle, I mean any set of the form A times B, so that A is a subset of, A and B are both subsets of 0, 1 to the n. Okay? Well, now, after this definition, an immediate meta question that one could ask is that, what is the relation of communication complexity with other natural complexity measures of your matrix? And one of the most natural measures of complexity is rank of the matrix over the real numbers. So one of the most important conjectures in the area is Lowas-Sachs, is given by Lowas and Sachs, called log-rank conjecture, that says communication complexity is always bounded by polylogarithm of rank of the matrix. All right. Well, this conjecture has been studied for a long time, and people have been trying to prove that it's hard. So people are looking at different classes of interesting classes of functions to solve the conjecture, at least for those classes. And one of these most important classes is called XOR functions, or XOR matrices. So let me just define what an XOR function is. So suppose you're given a function from f2 to the n to 0, 1. By f2 to the n, I mean the n-dimensional vector space over the finite field with two elements. So you can just naturally identify it with 0, 1 to the n. Now, when you have such a function, you can immediately get a matrix from that, and that's the matrix is from f2 to the n to f2 times f2 to the n, and on x and y, you just define f of x plus y. So this plus is just the XOR, the bitwise XOR of the input variables. Okay, here's an immediate observation that if your matrix that's defined in this way is constant on A times B, then this implies that your function is constant on A plus B, on the sum set of A plus B. And A plus B is defined by the sum of all pairs of elements that small a comes from A and B comes from B. Okay, so that's a set in f2 to the n. All right. Well, now, okay, now that we have this function, our meta question changes to the following. What is the communication complexity of the matrix? And what is the relation to complexity measures of the function rather than the matrix? And one of these interesting complexity measures of functions is called parity decision tree complexity. So let me just define what a parity decision tree is. You have, again, an input, n-bit input from f2 to the n. And a parity decision tree is just like a decision tree, but in a typical decision tree, in a standard one, you would ask variables as questions. But here you ask parity of a bunch of input bits. So you just add some of these input bits, and you computed mod 2, and you look at the results. Depending on whether it's 0 and 1, go to the left and right. So this, anytime I'm using addition, I mean XOR. This is the operation on XOR. And parity decision complexity of a function is defined as the shortest parity decision tree that would compute your function. Okay? Well, here's an interesting observation that communication complexity is always bounded by twice, at most twice, a parity decision tree. Why? Suppose you have your XOR matrix that's defined in this way. Well, x and y, this is just f of x plus y by definition. Let's say x plus y is z. So suppose we have a parity decision tree for f. What does that mean? It means we have this parity decision tree for f, and we want to get a communication protocol out of it. So we can just write this z1 plus z4 plus z5. You can just separate it. First substitute xi plus yi instead of zi, and then separate it. So we get this plus this. But Alice has this part, always, because that's the input of Alice. And Bob always has this. So they can just communicate this sum and this sum. They can exchange these two, and then just add up so they both know what is the result of this node. Since they both know, they could just move on the tree and then ask the next relevant question. And this, because for every node we do 2 exchanges, then the communication complexity is bounded by at most twice of parity decision tree. But the question is, okay, but well, we know this is bounded above, but could it be much smaller than parity decision tree? And in this work, we do show the following. We show, no, actually, indeed, that these 2 measures of complexity are equivalent, which means parity decision tree is always bounded by communication complexity to the power, like to the 6. All right. And this has an immediate corollary. That means the log-rank conjecture for XOR functions is equivalent to the following conjecture that was given in 2013 by Zhang, Wang, Xie, and Zhang. They, as an approach to prove log-rank conjecture, they made this conjecture that parity decision tree is always bounded by polylog of rank of the matrix. But since we know parity decision tree is also bounded by this, then this implies that these 2, if you prove log-rank conjectures, that would just also imply this one. All right. So let me just go into the proof sketch. Well, again, as a reminder, we are given a communication protocol, and we want to construct a parity decision tree for our function. Okay? Just look at this parity decision tree for a bit. What is every leaf? So every time that we ask a question, it's like we're cutting our space to half and go either to the left or to the right. Right? And so every tree corresponds to a subspace of our space of f2 to the n. And by subspace, I mean an affine subspace. And the codimension of your subspace is just the depth of your leaf. All right? So an interesting observation that was made in the same paper that I mentioned is that to construct a parity decision tree for your function, it's actually enough to just find one big subspace. And why is that? Because you can find one big subspace such that your function is just constant on that subspace. Then your function would simplify on all other cosets of your function. And so just, you should know that now the goal is just to find a large subspace that our function is constant on, and that would immediately give us a parity decision tree for our function. Okay? So this is our only goal. Find a large subspace such that it's constant. Okay, so now we're looking for that subspace. Well, the first natural approach is just to look at the largest rectangle that we have. We know that this rectangle corresponds to a subset. A and B corresponds to subset A plus B, and just try to find a large subspace inside that one. So one could hope that we could have a conjecture of this form, that if whenever you have 2 big sets, then there should be a large subspace inside A plus B. But unfortunately, this is false. So here's a counterexample: a Hamming ball. So if you take AB to be both a Hamming ball of radius, let's say n½ minus square root n, both of these, this is a big set, but A plus A doesn't contain a large subspace. You can easily show that. Well, okay, so the thing is, what do we do now? This, of course, doesn't work. Well, here's an idea. We can just look for a subspace that's almost inside our rectangle. So just focus on the biggest rectangle and find a subspace that's almost inside of that. And as long as this error is very small, since we know that... Okay, let me explain again. If we could find a subspace that's almost all of it is inside a rectangle, then if the error was very small, based on uncertainty principle, this should immediately imply that the function is actually constant on our subspace. Why? Because what is uncertainty principle is just a simple observation in additive combinatorics. You can say that if a function has low rank or the Fourier coefficient has small support, then its average cannot be too small and too large. So if we find a subspace that's almost all of it 0, it actually has to be 0. And that's all we were looking for. But, well, we need a good error bound. But, well, the problem is this requires proving this conjecture in additive combinatorics. That's very interesting and would have some other very interesting consequences. So here's the conjecture. It says whenever you have two sets A, B that are at least like alpha fraction of all of your space, for every epsilon you could find a subspace inside A plus B, almost inside A plus B, 1 minus epsilon fraction, such that codimension of your subspace is bounded by a polylog of the error parameter and the density of your sets. This is a very interesting question that, well, we don't know how to prove, so we can't use this approach. By the way, now we're talking about A plus B, but this is known for, if instead of A plus B we were talking about A plus B plus C. So if you have 3 sets A plus B plus C, this would, in this paper by Shou and Sisak, they show that it actually has subspaces almost all contained in that. Okay, we don't have that, but we have the following result by Sanders that says this proved the same thing, but not with arbitrary small epsilon, but with like a constant epsilon. So if your epsilon, let's say, is 1%, then you can always find a subspace of codimension that has polylogarithmic dependence on density of your function. And V intersection A plus B is almost all of your subspace. Okay? So our approach is to use this theorem, this weak theorem somehow, which wouldn't immediately give us the solution. Okay, so that's how we use that theorem. Well, the general idea is we should somehow utilize the entire partitioning structure of our matrix, right? We're not just focusing on one rectangle. Okay, so here's a rough idea. First, suppose that your function has like average bigger than half, at least. Well, we know it has, even though it has average over the half, it can't be all 1, right? So there should be one rectangle that is all 0. So we found this rectangle that's all 0. It's big. Now we use the Sanders result that I just explained and find this subspace that has a large intersection with this rectangle. Like suppose 99% of this subspace intersects with this rectangle, so its average is less than 1%. Okay. Now let's see what can we do. We can just look at all the partition of this whole matrix to all the cosets of the subspace. And somehow we want to prove that, well, on a typical coset here, one of the partitions restricted to that coset, one of them at least will be much simpler. So we can just focus on that one and recurse. So we can just restrict to, for example, this one, suppose became very simpler for some notion of simplicity. And we can just focus on that one, and we just continue until it's so simple that it's just constant. All right? Okay, now all I should explain is that what do I mean by simple and how do you get a simpler coset, right? So, well, here's a partition we have from the beginning. We have our matrix is partitioned into rectangles. Suppose I'm just picking a random point from my matrix. So I'm picking x's randomly and y's randomly. And suppose I had a random variable that would give me the index of the rectangle that contains that random point. So in this example, pi is a random variable, and phi of xy is 5, because my index is 5. All right. Now, what did we have? We had that, first we had that our function had high average in total, and we knew that we found this subspace that has very low average, right? Now let's see what we know. If we knew that our point, our random point, is inside this subspace that had low average, then that should mean that the point shouldn't be inside a rectangle that was 1, right? Because there are not many 1 rectangles in that. The probability of getting a 1 rectangle is very low because its average is mostly 0. And I just want to emphasize that when we find a subspace V inside F2 to the n that our average was low, that immediately implies that, suppose this was V, so V times V has a low average. That means V plus W times V plus W is also the same thing, because these are exactly the same thing, because V plus W plus V plus W is just V. So when you find a subspace that has low average, you just immediately found all these other cosets that are in the diagonal, they all have the same low average. And now we know that if we pick points randomly, conditioning on that our point is inside one of these cosets, it gives us information about the protocol, about this random variable. It tells us that its value should not be coming from a 1 rectangle. It should be most probably in a 0 rectangle. Okay, so what does it mean that it gives us information about this? It means that it's conditioning on this, the entropy of our random variable decreases, right? So that's the main lemma of our result that we use heavily. We say anywhere that you have a function and you can find a subspace that the difference between this average and the average over the subspace is far apart, then if you look at the entropy of this random variable that I just explained, and you average it over all its restriction to different cosets. So for each random variable, you just restrict it to every coset, and you average it over all cosets. This average drops by like epsilon squared compared to the entropy of the whole space. Okay, and so what do we have? Every time we can start with an epsilon. That, let's say, you can use Sanders' result always with epsilon equals 99%, or let's say 75%, or anything. So anytime we get a constant reduction in entropy, right? And what is the beginning entropy? Which entropy do we start from the beginning? It's just, well, we knew we had a partition to 2 to the k many rectangles, so entropy could be at most k. Every time we drop it by a constant, so it requires at most just order of k many reductions. Okay? So that just finishes the result. So let me explain some open problems. Well, the first natural open problem is, can we extend this result to randomized parity trees? So suppose you are given a randomized communication complexity, a matrix with low randomized communication complexity. Can you give a randomized parity decision tree for your function? And the other question is, okay, we were focusing on XOR functions, but what about other classes of functions? And for example, one of these interesting classes of functions is AND function, which is just bitwise AND of the variables. So, for example, if you are given an AND function with low communication complexity, can you say that it has low decision tree in some interesting decision tree model. For example, a natural candidate for this is an AND decision tree. A decision tree that instead of asking like parity of some of the bits, you ask AND of some of the bits. So this is an interesting question. All right, thank you. Yeah. Yes. Oh, yeah, good question. Well, I have no guess about this, but at least we know that this approach that we took, there's really no way that we could improve this balance of 6. Because we already lose a factor of power of 4 because we use Sanders' result, and that's any improvement on that would be a big achievement. That's very interesting. We lose 1 log factor again for the entropy reduction. So what do we get? We get a subspace of codimension log to the 5, poly-log to the 5. And the other log factor that we lose is because, well, we haven't found a parity decision tree yet. We've just found one subspace. So every time you find a subspace, you have to continue on all other cosets and also do a reduction, continue on those. And because every time if you found a constant subspace on every other coset, the rank of your function drops by 2, then every time you do this rank reduction, you also get a log factor there. But I don't know which side it should be closer to. I don't know. No, because we need something. It's totally different from PFR because this conjecture really, if you had the best PFR, you couldn't say anything about this, or we don't know how to say anything about this with using PFR. And this also doesn't say anything about PFR. So apparently these are not very relevant. Because PFR could talk about, let's say, bigger sum sets, not just A plus B. Yes? And what? Deterministic and randomized parity decision tree? No, I don't think that's possible. You could. I mean, it's assuming that like randomized communication complexity was equivalent to randomized parity decision tree. We don't know really. I don't know. I don't think there should. Yeah. Is randomized is low? Yeah. So yeah, there should be.